Hello, class. Okay, so today we're going to talk about what happens when electromagnetic radiation enters a transparent medium. So yeah, we know that there's a lot of mediums that light can pass through. Just one example would be glass. Otherwise, windows wouldn't be very practical. Water, another example. If you go underwater, you can still see. So we know that light can travel through water. Now, on a fundamental level, trying to explain what's happening is extremely complicated. There's, the oscillating electric and magnetic fields are interacting with the charges in the matter. So, mostly it's the electric fields that have a significant effect. But we're not going to get into too much detail. What we're going to do is we're going to look at the case where light travels from one medium to another. So let's say light, we have an incident ray. So let's say this is air, and this is some other medium like water. So what happens when this, we're representing this as a ray. We can also represent these as wavefronts, but for now, what happens when air goes to water? It's interesting, despite how amazingly complicated this is, because matter itself is very complicated. You can have like a simple thing like a crystalline solid, where you have just like atoms that form these periodic arrays. It's about the simplest kind of matter. But if you look at something like glass, it's much more complicated. If you look at it on a molecular level, amazingly, we can describe the interaction of light and matter to a large extent. We can explain that with one number called the index of refraction. And we call this number n. And we define it as c over v, where c is the speed of light in a vacuum, and v is the speed of light in this particular medium. So we say that light goes slower in other mediums. So nothing can beat the speed of light in a vacuum. Nothing can travel faster than that. But we say like when air goes into water, or the light goes from air to water, it's going to slow down when it enters the water. Now, technically, light can never speed up or slow down. It just, when it exists, it goes the speed of light. What happens when light enters the water is these photons can get absorbed by the molecules and re-emitted. And so there's that little delay between getting absorbed and re-emitted. But effectively, we're going to say it's going slower. So v is the speed of light in the material, in the medium, whatever it is. And because the speed of light is always, in the medium, is always less than in a vacuum, n is always greater than or equal to 1. Let's write that down. Now, n equals 1 only for a vacuum. In any other medium, n is greater than 1. However, if you look at air, let me actually look this up. For air, we have 1.000293. So basically, as far as we're concerned, the index of refraction for air is just 1. You need 5 significant figures to notice a difference. We'll just say that's equal to 1. But, in theory, every medium, light's going to slow down at least a little bit. So let's look at we'll write down a few examples of index of refraction. Okay, but as far as calculations are concerned, n is 1 for air. Now, another important one is water, which is around 1.33. going to look at N for glass. So let's see, water, yeah, 1.33. Glass, about 1.5. Again, there's different types of glass. Let's just say 1.5. So different indexes of refraction. So light travels fastest in air, a little bit slower in water, and slower still in glass. Okay. Now, other than the slowing down, what effect is this going to have when light goes from, say, air to water? Well, it turns out it's going to bend. And I'm going to draw this. So if you remember in mechanics, say you have a wave on a string, and you oscillate it back and forth, and then it hits the wall and bounces back. Yeah, we're going to have a reflected ray. Let's call this theta 1. So light is going to hit this boundary with an angle theta 1. There's going to be a reflection, which is also at that angle theta 1. And then there's going to be a refracted ray that makes an angle theta 2. Okay, and we want to know what is the relation between these two angles. And we'll need to know the two materials to do this. So to start out with, we can say that C is equal to N times V. Now C is the speed of light in a vacuum, that's constant. So we can say in this medium, N1 times V1 equals N2 times V2. Because they're both equal to the speed of light. Remember, the speed of a wave is the frequency times the wavelength. So we can replace V with frequency times wavelength. And for now, I'm writing them F1 lambda 1, F2 lambda 2. However, it turns out the frequency is not going to be affected by moving from one medium to the next. So we don't need to distinguish these two different frequencies. And what we have is this ratio, N1 over N2 equals, N1 over N2, that would be V2 over V1. So let's look at this. Let's say this is air, and this is glass. What's going to happen to this light when it enters this we're going from N equals 1 to N equals 1.5. So N1 over N2 is going to be less than 1 in this case. We have like 1 over 1.5, that's definitely less than 1. And so that would mean V2 is less than V1. So it's going to slow down when it enters the second medium. And again, that's assuming that N2 is greater than N1. Okay. So if you're going from a low index to a high index, the light slows down. Now what's going to happen to this angle? That's what I want to draw this picture. I think I want to get rid of, let me just redraw this. So we have just what we need. Because I want to draw the wavefronts as well. So we've got our normal line here. This is where the light's going to hit. So we have our wavefronts that would look like this. So this is lambda 1. Okay. And this was our angle we were calling theta 1. Here we have N1. Okay, so yeah, the wavefronts are separated by the wavelength. And then we enter this medium, N2, which is, in this case, the way I'm drawing it, N2 is greater than N1. This was what we defined as theta 2. And how do the wavelengths relate to each other. Let's go back. Well, here, let's go with here. Let's just look at, say this is 1, N2 is 1.5. The numbers don't matter so much, just that N2 is bigger than N1. So just, that's all we care about with these numbers. And let's write down this, just in case. So remember, the speed of a wave is a frequency times the wavelength. Now the frequency is the same in both cases. The frequency is not affected by going from one medium to another. And so we could write this as lambda 2 over lambda 1. So in the case we drew here, this ratio, N1 over N2 is less than 1. That means lambda 2 is less than lambda 1. So we've got these smaller wavefronts here. So the wavefronts are perpendicular to the ray. So they're going to look like this. They're smaller. So these are the wavefronts for the second, we call this the refracted ray. And so we want to use that to find, now it's kind of a geometry problem. We want to find the relation between these angles. And so if we look at just from here to here, like this distance here is lambda 2. The wavelength in the second medium. So yeah, these wavefronts go in both directions. So that's lambda 2. And we want to relate that to, you would say this is theta 1. Remember, the wavefronts are perpendicular to the rays. So this is a 90-degree angle here. So this is 90 minus theta 1, which makes this angle theta 1. Okay, so then we have this triangle here. Actually, yeah, let's extend that. So let me redraw this picture. Let's just draw this first part. Yeah, so the next wavefront, same distance, it's going to land there. And then this is going to be lambda 2 here. So the new ray is perpendicular. So that's a right angle. So this is the refracted ray. So kind of looks like it just goes in a straight line, but there is some bending there. This is theta 2. And yeah, this here would be lambda 2. So again, these are parallel lines. This is lambda 2. Okay, so yeah, then we could draw, more wavefronts. We want to just focus on what we have here. So again, this is lambda 1, and this is theta 1. Sure, this is, like say this is 30 degrees. Because we have a right triangle, that would make this 60 degrees. And again, this is a normal line, and that's our surface, so that's a right angle. So that's also theta 1. Okay, so what we can say from this picture, they share we have these two triangles here. This is a right angle because it's between the wavefront and the ray, so those are perpendicular. So if this is theta 2, Again, another right angle. This is 90 minus theta 2, which makes this one theta 2. Okay, so these two share this side here. We can call that H for hypotenuse, because again, right angles. So opposite the right angle is hypotenuse. So we can say sine of theta 1 is equal to lambda 1 over H. And we can say sine of theta 2 is lambda 2 over H. Yeah, so sine of theta 1, that's opposite over hypotenuse. Sine of theta 2 is opposite, which is lambda 2 over H. And then we can put these together, like H is lambda 1 over sine theta 1 equals lambda 2 over sine theta 2. We're almost there. But yeah, I guess we'll write that down. So we have lambda 1 over sine of theta 1 equals lambda 2 over sine theta 2. We want to get rid of lambda though. And yeah, I think we want to go back to kind of the start. We can say the speed of light is n times v, which is n times frequency times wavelength. And so because the speed of light is constant, we can say n1 times f times v1 equals n2f v2. Cancel out the f. Oh wait, sorry, that should be lambda 1. Frequency, the speed is frequency times the wavelength. So here, lambda 1, let's do it this way. Lambda 1 over lambda 2 equals sine of theta 1 over sine of theta 2. And over here, we can see that lambda 1 over lambda 2 is n2 over n1. So now if we just rearrange the terms, we have n1 sine theta 1 equals n2 sine theta 2, and that's the final form we wanted in. This is called Snell's Law, and it relates the index of refraction to the angles of, the index of refraction, or this is the angle of incidence, that's the angle of refraction. That relates those to the two materials. So all we need to know is the index of refraction for each material, and then if we know one angle, we can find the other. Okay, so we've got our result over here. Took a little work to get there, but now that we have that, let's erase the board. Now you can see in this example, we're able to see that, we went from a low index to a high index. And because the wavelength shrunk here, it kind of forced this ray to bend towards the normal. Like if there was no medium, the light would have just kept going in this direction here. Except when it went into the material with a higher index of refraction, we say the ray bends towards the normal. Where if we went the other way, and again, we could just reverse it. So if you had light going this way, again, if it kept going in this direction, or if there's no change in material, it would just keep going in this direction. But because it went from a high index to a low index, it bends away from the normal. Now, you can remember that if you want. It's actually worth remembering. I'm not a big fan of memorizing things, but in this case, it doesn't hurt. But if you happen to forget, it's easy to figure out just from looking at Snell's Law. So yeah, let's just look at an example. Say we have n equals 1.2 and n equals 1.4. So we're going from a low index to a high index. It's very commonly the case because we usually go from like error to some medium. So yeah, it's usually what happens. But anyways, let's say you don't remember if it's going to bend towards the normal or away from it. So here's n1 and n2. Here's theta 1. Theta 2 is unknown. We don't know how to draw it yet. But just from Snell's law, we can say sine of theta 2 is n1 over n2 times sine of theta 1. And n1 over n2 is less than 1. So sine of theta 2 is less than sine of theta 1. Now, the way we're drawing these pictures, we're always dealing with angles between 0 and 90 degrees. And so if theta 2 is less, or sine of theta 2 is less than sine of theta 1, we can definitely say that theta 2 is less than theta 1. So theta 2 is going to be a smaller angle, so we can see that we're bending towards the normal. Okay. So there's actually an interesting example I want to look at, though. Let's say we go from a high index to a low index. Let's call this theta 1. So I'm just totally making up these numbers. Say we go from a material with index 1.6 to an index of 1.1. We know we're going to bend away from the normal. And I want to actually make a table. Like theta 1. And then I want to calculate theta 2 using Snell's law. So let's start with this. Sine of theta 2 is going to be n1 over n2 sine of theta 1. Let's actually do this. 1.6 divided by 1.1. Let's just do that. It's about 1.45. Give me 1 second. Sorry about that. Okay, so we can solve for theta 2. That'd be the inverse sine Okay, so basically we're going to plug in theta 1, multiply it by 1.45, and then take the inverse sine, and that'll give us theta 2. Let's start out with 10 degrees. So let's see, we want the inverse sine of 1.45 times sine of 10 degrees. And that's about 14.6. Okay, let's go to 20 degrees. I should actually be doing this. I don't want to just write down the answer, actually. I want to put an intermediate step. So let's do this. Let's do it for the middle column. let's do it like this. Okay, so what I'm going to do is say 1.45 times sine of 10 degrees. That's about 0.25. And then if we take the inverse sine of that, we get 14.6. Okay, let's go to 20 degrees. So 1.45 times sine of 20 is about 0.496. That's about 0.5, so that would be, I know just sine of 30 is 0.5, close enough. Now let's go to 30 degrees. It's about 0.725. So we take the inverse sine of that. It's about 46.5. I assure you there is a point to this. Let's try 1.45 times sine of 40 degrees. Okay, if we do that, that's 0.932. And so then we take the inverse sine of that. 68.7 degrees. And let's do 50 degrees now. So start out 1.45 times sine of 50. We get 1.11. Okay. Now what happens if we take the inverse sine of 0.11? Our calculator gets mad at us. So we can't do it. Again, if we plot sine of x as a function of x, remember it's between 1 and -1. It only lives between those two values. So by taking the inverse sine of 1.11, we're saying what value of x is going to give us a sine value somewhere up here, and there is no answer to that. And so, yeah, basically what happens physically here is if we shine light with an angle of incidence of, let's start with 10 degrees, it bends away from the normal. As this increases, as our angle of incidence increases, this increases as well. And eventually, we're going to reach a point where there's a certain angle here where the theta 2 is going to be 90 degrees. That means the refracted ray is going to be right along this boundary, which means that none of the light is actually transferring into this second medium. So you've got light that just hits the surface and bounces off. Nothing enters this region. But that's only if light enters with a big enough angle. And we call that the critical angle. And if you look on your equation sheet, there is nothing that tells you the critical angle isn't mentioned on there. And the reason it's very easy to figure out what it is, just using Snell's law. So the critical angle, that just means the index or the refracted angle is 90 degrees. So if we want to find the critical angle, we have n1 times sine of theta c equals n2. And again, this is the angle that will give us a refracted angle of 90 degrees. And sine of 90 degrees is 1, so that's it. So we have sine of theta, sine of our critical angle is n2 over n1. Then we just take the inverse sine. Let's actually do that once. It'll be somewhere between 40 and 50 degrees. So let's see, inverse sine of 1.1 divided by 1.6 Yeah, it's 43.4 degrees. So again, yeah, if we plug in that angle, the refracted angle is going to be 90 degrees. And this is called total internal reflection, because there's no ray that goes into this second medium, but you always have this refracted ray. So it's called total internal reflection because the light's still being reflected internally because it's going back into the initial medium that it was coming from. So yeah, that only occurs if the angle is equal to or greater than the critical angle. It's actually a really interesting application of this. You got these two kinds of plastic, like really bendy, flexible kind of plastic. Yeah, let's just get rid of everything. So yeah, this is like, imagine two cylinders, one surrounded by the other. And what you do is you shine light, and it bends on going into this first medium. And then when it hits this boundary, it hits it with greater than the critical angle. So it just bounces off that, then it hits the other end, and it just keeps bouncing around, in this inner part. This is called the core, and this is called the cladding. Again, there's just different, they're just mediums with different indexes of refraction. And so this light just keeps bouncing around inside, and it can travel without much energy loss because of that. And this is kind of a very, basically this is a fiber optic cable. Reportedly, the story goes that the person who invented this, he was a grad student, and this was his PhD thesis, and the school said, that's a great idea, we want to buy that from you, and they offered him $1 million, and he took the money, and he got totally ripped off, because fiber optic cables are worth a lot more than that. This is how we communicate. We used to send signals electrically, like an old phone line. You can send electrical signals and contain information in those signals. But with fiber optic cables, they're just much more efficient, and you can send much more information with these cables, just working with light as opposed to electricity. And so yeah, this fiber optic cable idea, this was worth way more than $1 million. Of course, real fiber optic cables are more complicated than just what I've described here, but yeah, very, very good idea. I'm sure whoever invented it's doing just fine, but could have probably made a lot more money if they held out. But anyways, I think that's it for Snell's Law. Yeah, we're going to use Snell's Law later as well. One important application of bending light is we can design, say, a glass material that is curved. And so imagine light enters, we have some parallel beams of light, and then they're going to bend, and we can create a converging lens like this. So if we have parallel beams, we can cause them to converge and focus them at a point. And a very important application of this is if you put an ant there, you can burn it. Don't actually do that, but probably heard of that magnifying glass, and you can light paper on fire even by concentrating enough sunlight in a small area, but also for magnifying images. And using more than one lens, you can create devices like telescopes and microscopes. So yeah, lenses, very, very important as well. So that's what we'll talk about next, focusing light with lenses. This would be called a converging lens. We can also have like an hourglass shaped lens, where if you have light coming in parallel, there'll be, this is called a diverging lens because the beam's spread out. So, and again, there's a lot of different types of lenses you could design, but very important devices. And it really is based on Snell's Law. Over here, light bends going from air to glass. And so you just have to get the right shape, and you can make lenses like this. Okay, but that'll be it for this one. So actually talking about lenses, that'll be a separate lecture. So we'll stop this one here.